Welcome to the Deep Dive. Today we're going to dive into something that I find pretty fascinating, and I hope you will too.
Okay, sounds good.
Way back in 1890, there was a guy named J.F. Herbart, and he said something that I thought was pretty cool about what we're going to talk about today.
All right.
He said, "There is perhaps nothing which so occupies the middle position of mathematics as trigonometry."
Oh, wow. Okay, so what is that?
Yeah, so that's what we're going to be talking about today, trigonometry.
Okay.
And
That does sound kind of central.
it is. That's a good way to think about it, right? Kind of a
Yeah.
hub that connects all different kinds of mathematical ideas, right?
Yeah, absolutely.
So for today's deep dive, I've brought some, I think, pretty interesting real-world scenarios that can demonstrate the power of trigonometry.
I like it.
Yeah, so it's very easy for math to feel abstract, right?
Sure.
But trigonometry really gives you the tools to answer some
Oh, cool.
practical questions.
Mhm.
So, picture this.
Mm-hmm.
You're a student. You're looking up at the Qutb Minar.
Okay.
How could you figure out its height without actually measuring it?
Oh, that's a good question.
Right.
Though.
Or, say, you're on a balcony, you're high above a river,
Right.
and you see a flower pot on the opposite bank.
Okay.
If you know how high your balcony is,
Right.
could you determine how wide the river is?
Hmm.
And then what about, tracking a hot air balloon?
Right.
How could we find its altitude at different points during its flight?
Yeah, these are challenging, seem
Right.
like challenging things to solve directly.
They do. And that's exactly where trigonometry comes in, right?
Right.
It gives us the tools, the techniques to
Yeah.
figure this kind of stuff out.
I like it.
Okay, so let's break down this word for a second, right?
Okay.
Trigonometry. Sounds a little intimidating,
Yeah.
maybe, but the roots are pretty straightforward, right?
Right.
So the word itself comes from Greek. Tree three. Gon, sides, and metron, measure.
Okay.
So really, it's the study of the relationships
Yeah.
between sides and angles.
Right.
Triangles, pretty simple.
Yeah, I like it. Triangles, we've all seen those.
We have, and this isn't anything new, right?
Right.
This stuff goes way back.
It does.
Yeah. So we know that, ancient Egypt, Babylon, they were working on trigonometry.
Wow.
Astronomers, right, the early astronomers, they were using this to figure out,
Okay.
the distances to stars
Wow, that's
and
incredible.
planets. Pretty wild, right?
Yeah. Just thinking about how far away things are using triangles, that's amazing.
Yeah, pretty cool. And it's not just a historical thing, right?
Right.
It's still important today in our modern world, especially
It is,
for
like engineering.
physical sciences.
Absolutely.
The stuff that we rely on every single day.
Right. The tech that we use, a lot of times without realizing it.
Yeah, absolutely. So for today's deep dive, we're going to focus specifically on trigonometric ratios
Okay.
of acute angles in a right triangle.
Right.
But so much more to trigonometry, right?
Okay,
We can look at all kinds of angles, 0 degrees, 90 degrees. We could look at trig identities.
So we're building like a foundation today.
Yeah, exactly.
Okay.
So picture this. We've got a right triangle, right?
Okay.
We'll call it ABC, standard stuff, right?
Right.
So A, B, and C are the corners. B is the right angle.
Got it.
Now, pick one of the acute angles. So either A or C, doesn't matter. We'll say A.
Okay. A.
So we got to identify the sides now in relation to this angle A, right?
Okay.
So the side opposite angle A, the one is directly across from, we'll call that BC.
Okay.
The longest side, of course, is always the hypotenuse. That's AC.
Right. Opposite the right angle.
Yeah, exactly. And then the side that forms angle A along with the hypotenuse, that's AB.
Okay.
That's the side adjacent to angle A.
Got it.
So opposite, hypotenuse, adjacent. Got to remember those.
Absolutely.
They're really important.
Okay.
Now, if we were to shift our focus to angle C,
Okay.
these opposite and adjacent sides, they switch, right?
Oh, okay.
But luckily, the hypotenuse always stays the same.
Right. Okay, good.
So that's nice. So now, with these sides, we can define count them, 6 fundamental trigonometric ratios.
Oh, wow. 6. Okay, lay 'em on me.
Okay, so the first one is sine of angle A. We shorten it to sin A.
Sin A. Okay.
It's the ratio of the length of the opposite side, BC, to the hypotenuse, AC. So sin A equals BC over AC.
Okay.
Opposite over hypotenuse.
All right. Opposite over hypotenuse. Got it.
Next up, cosine of angle A, cos apsu A. This is the ratio of the adjacent side AB to the hypotenuse AC.
Okay.
So cosec AA equals AB over AC, adjacent over hypotenuse.
All right. Adjacent over hypotenuse makes sense.
Then we got tangent of angle A, tan A.
Yes.
This is the ratio of the opposite side, BC, to the adjacent side, AB. So tan A equals BC over AB, opposite over adjacent.
Opposite over adjacent. Okay.
Yeah.
I'm starting to see a pattern here.
There's a pattern. There are three more,
Yeah.
and they're basically reciprocals of the first three.
Okay.
So cosecant of angle A, cosec A is 1 divided by sin A.
Okay.
So cosec A equals AC over BC.
All right.
Hypotenuse over opposite.
Hypotenuse over opposite. Okay.
Second of angle A, sec A, is 1 divided by cosec.
Okay.
So sec A equals AC over AB. Hypotenuse over adjacent.
Hypotenuse over adjacent. Got it.
And finally, cotangent of angle A, or cot A, is 1 divided by tan A.
Okay.
So cot A equals AB over BC, adjacent over opposite.
Adjacent over opposite. All right. So we got the three, main ones, and then the three that are kind of like the flip side.
Exactly. So sine, cosine, tangent, and then they're buddies.
Right.
And our source also points out, there's some key relationships here, right?
Okay.
So tan A, you can also express it as sin A divided by cos A, right? And cot A, you can express as cos A divided by sin A.
Okay.
So they're all, kind of connected.
We're all related. All right. So how about this? It's pretty cool how these ratios kind of capture the relationship between an angle and the proportions of the sides, right?
Right.
And I was kind of looking at where did these words come from?
Oh, yeah.
Like sine, cosine, tangent.
It's kind of interesting. The word sine, it's got this interesting history.
Oh, okay.
So it goes all the way back to this Indian mathematician, Aryabhata, 5th century AD.
Okay.
He used this term, ardhaja, which basically means half chord of a circle.
Okay.
And then that got shortened to ya, or jiva.
Right.
Then this got translated into Arabic. They kept that word jiva.
Mm-hmm.
But then when it was translated into Latin, jiva sounded kind of this Arabic word jaib, which meant curve or bay.
Huh.
So they translated it as sinus, which also in Latin means curve or bay.
Oh, okay.
And eventually sinuses became sine.
So from half chord to curve to sine.
Okay. Yeah. And then Edmund Gunter, this English astronomer, 17th century, he's the one who started using sin, the abbreviation.
Okay. All right. What about cosine and tangent?
Yeah, they came later. Cosine, it arose from the need to find the sine of the complementary angle.
Okay.
So 90 degrees minus the angle.
Mm-hmm.
Aryabhata, he called it cotija.
Okay.
And Edmund Gunter, he came up with cosinus.
Okay.
And Jonas Moore, another English mathematician, he started using cosine in the late 17th century.
Okay.
Tangent also came later.
Got it.
But one thing our source points out that I think is really important, when we write sin A,
Right.
we're not multiplying sin by A.
Right.
It's just, it's one thing. It's the sine of angle A.
It's shorthand. Right.
Exactly.
Mm-hmm.
Okay, so now let's say we have different right triangles, but they all share the same acute angle A.
Okay.
So imagine we pick a point P on the hypotenuse AC, or even extend AC to a point Q. So now we got these new right triangles, PM and QAN.
Right.
What do you think happens to the trigonometric ratios of angle A in these new triangles?
I don't know. Does it get more complicated?
It seems like it should, right? But our source says that it doesn't.
Oh, okay. Good.
Yeah.
So why is that?
So remember similar triangles.
Right. Yeah.
Triangles PAM, CAB, and QAN. They're all similar because they share angle A, and they each have a right angle.
Okay.
And a key thing about similar triangles,
Yeah.
their corresponding sides are proportional.
Right.
So that proportionality, that's what keeps the ratios of the sides,
Okay.
which are trigonometric ratios,
Right.
the same.
Oh, okay. All right. So even though the triangle's a different size, it doesn't matter.
Exactly. As long as the angle A is the same, the ratios are the same.
Huh. That's pretty cool.
It is.
So it only matters what that angle is.
Yeah.
Okay, cool.
Pretty powerful idea, right?
Yeah, definitely.
So a quick note on notation. When we write sin A,
Okay.
that just means sin A.
Right.
Same for all the other ratios.
Okay.
But don't confuse that with sin A. That's different. That's a whole other thing.
Okay.
Okay, so now, what if we know just one trigonometric ratio
Oh,
for an
yeah.
acute angle? Could we figure out the other 5?
I don't know, maybe. Could you?
Yeah, you can. Because remember, all these ratios are interconnected through
Yeah.
the sides of the triangle.
Right, yeah.
So if you know one, you can figure out the relationships between the sides,
Right.
and then you can find the rest.
Okay.
And a common way to do this, you can use the Pythagorean theorem.
Oh, okay. Right.
So,
right.
for example, let's say we know that tan A equals 43.
Okay.
How would we find the other ratios?
So how would we do that?
So if tan A equals 43, that means the ratio of the opposite side BC to the adjacent side AB is 4:3.
Okay.
So picture a right triangle where BC is 4 times some constant, we'll call it K.
Right.
So BC is 4K.
Okay.
And AB is 3 times that same constant, so 3K.
3K. Okay.
Now, to find the hypotenuse, AC,
Okay.
we use the Pythagorean theorem. AC tree equals AB plus BC through, which is 3K plus 4K. That simplifies to 9K toward plus 16K, which is 25K.
Right.
And if we take the square root of both sides, we get AC equals 5K.
5K. Okay.
So now we know all three sides. BC is 4K, AB is 3K, AC is 5K.
Got it.
And we can find all the ratios.
Yeah.
So sin A is BC over AC, which
Right.
is 4K over 5K, which is 45.
Yeah.
Cos A is AB over AC, 3K over 5K, which is 35.
Right.
And you find the rest. Cosec, a second, cotangent, all that.
Got it. And you see how the day just cancels out, right?
Yeah, exactly.
Which means it doesn't matter what the actual side length is.
Exactly.
Yeah.
Just the ratio matters.
Okay.
So there's also this little remark in our source that says sin A and cos A
Okay.
in a right triangle are always less than or equal to 1.
Oh, okay.
Why do you think that is?
Why would that be?
Well, think about it, right? The hypotenuse is always the longest side.
Right.
And sin A is opposite over hypotenuse.
Right.
Cos A is adjacent over hypotenuse.
Right.
So the numerator is always going to be less than or equal to the denominator.
Oh, yeah. Okay. That makes sense. So the ratio is always going to be less than or equal to 1. Okay, good.
So now we've got another example here. It says if we have two right triangles
Yeah.
and they're acute angles, we'll call them B and Q,
Okay.
and sin B equals sin Q,
Right.
then angles B and Q must actually be equal to each other.
Oh, okay.
So why is that?
How does that work?
Again, it comes down to similar triangles.
Okay.
If sin B equals sin Q, that means the ratio of the opposite side to the hypotenuse is the same in both triangles.
Okay.
So let's say in one triangle, ABC, sin B equals AC over AB.
Right.
And in another triangle, PQR, sin Q equals PR over PQ.
Okay.
If these two ratios are equal, AC over AB equals PR over PQ, we can rearrange that to get AC over PR equals AB over PQ.
Okay.
We'll call that common ratio K.
All right.
Now, using the Pythagorean theorem in both triangles,
Okay.
we can find the third sides, BC and QR, in terms of the other two sides.
Right.
And guess what? The ratio of those third sides, BC over QR, also equals K. So all three pairs of corresponding sides have the same ratio, which means the triangles are similar.
Right.
And if they're similar, their corresponding angles are equal.
Oh, okay. That makes sense.
So B equals Q.
So same sign, same angle.
Exactly. Pretty cool, huh?
Yeah, I like it.
So our source gives a few more examples, like calculating expressions with
Oh.
trigonometric ratios and stuff.
Right.
But one thing I noticed in one of the examples, cos that plus sin that equals 1.
Okay.
That's always true.
Is that always going to be 1?
It is. It's a fundamental trigonometric identity.
Oh, wow.
We're going to talk more about those later, but this is like, sneak peek.
Okay, cool.
It's basically the Pythagorean theorem, but with trigonometric ratios.
Oh, okay. All right. So it's like the same idea, just expressed differently.
Yeah, exactly.
Hmm.
And then there's another example where 2 sin A cos A equals 1
Okay.
when tan A equals 1.
Right.
This just shows how these different ratios work together.
Right.
So when tan A equals 1, the opposite and adjacent sides are equal.
Okay.
That means A is 45 degrees.
Okay.
And if you plug in sin 45 and cos 45, you'll see the equation works.
Oh, okay, cool.
Yeah, and then the last example in this section, you got a right triangle.
Yep.
One side, and you know a relationship between the other two sides.
Right.
You got to find the sine and cosine of a specific angle.
Okay.
So you basically set up an equation using the Pythagorean theorem
Right.
and solve for the unknowns.
Okay, so it's all about like using those tools, those
Yeah.
basic definitions and the Pythagorean theorem
Yeah.
to figure out the stuff you don't know.
Yeah. And then exercise 8.1 is a good place to practice all this stuff.
Okay. So practice is important.
It is. Okay, so now let's look at some specific values, right?
All right.
30 degrees, 45 degrees, 60 degrees.
Okay.
How do we find the trigonometric ratios for these angles?
Yeah, how do we get those?
So these values, they're derived from geometry.
Okay.
Let's start with 45 degrees.
All right, 45.
So picture a right-angled isosceles triangle.
Okay.
So both acute angles are 45 degrees, right?
Right.
And the two legs, they're equal.
Right, equal length.
We'll say their length is A.
Okay.
Now, Pythagorean theorem tells us the hypotenuse is O plus A.
Okay.
That simplifies to a 2.
Let's see. Okay.
So now we have the sides. We can find the ratios.
Yes.
Sin 45 is opposite over hypotenuse.
Right.
over a 2, which is 1 over a 2.
Okay.
Cos 45 is adjacent over hypotenuse, also over a 2, so 1 over a 2.
Right.
Tan 45 is opposite over adjacent over a, which is 1.
Okay.
And then you can find the reciprocals, cosecant, secant, cotangent for 45.
Got it. So you start with the triangle, and then you can just figure everything out.
Yeah, exactly. Now, for 30 and 60 degrees,
Okay.
start with an equilateral triangle.
Okay.
All angles are 60, all sides are equal.
Right.
We'll say each side is 2a.
2A. Okay.
Now, draw a perpendicular line from one vertex to the midpoint of the opposite side.
Okay.
This splits the triangle into two congruent right triangles.
Right.
30, 60, 90 triangles.
Okay.
The hypotenuse is 2a. One leg is opposite the 30-degree angle.
Yeah.
And the other leg, using the Pythagorean theorem, is a veer.
A 3. Okay.
So now you have all three sides. You can find all the ratios for 30 and 60 degrees.
All right. So it's just like we did with the 45 degrees.
Yeah, same idea. You just use the sides and the definitions.
Right.
Okay, so what about those extreme angles?
Okay.
0 degrees and 90 degrees.
Right. Those are interesting.
Yeah, how do we think about those?
Yeah.
So for 0 degrees, imagine angle A in a right triangle getting smaller and smaller.
Okay.
As it approaches 0, the opposite side, BC, gets closer to 0.
Okay.
And the hypotenuse AC gets closer to the adjacent side, AB.
All right.
So at 0 degrees, sin 0 is BC over AC, which is basically 0 over AB, which is 0.
Okay.
Cos arrow is AB over AC, which is AB over AB, which is 1. Tan 0 is sin 0 over cos 0, 0 over 1, which is the 0.
Okay.
Now for the reciprocals, cos 0 is 1 over tan 0,
Right.
which is 1 over 0,
Okay.
which is undefined.
Right. You can't divide by 0.
Oh, can't divide by 0.
Yeah.
Sec 0 is 1 over cos 0, which is 1 over 1, which is 1.
Okay.
And cosec 0 is 1 over sin 0, which is also 1 over 0, so undefined.
Undefined.
Now for 90 degrees, imagine angle A getting bigger and bigger, closer to 90.
Oh, okay.
Now the adjacent side, AB, gets closer to 0,
Okay.
and the hypotenuse, AC, gets closer to the opposite side, BC.
All right.
So at 90 degrees, sin 90 is BC over AC, which is BC over BC, which is 1.
Okay.
Cos 90 is AB over AC, which is 0 over BC, which is 0.
All right.
Tan 90 is sin 90 over cos 90, 1 over 0, undefined.
Undefined. Okay.
Cot 90 is cos 90 over sin 90, 0 over 1, which is 0.
Okay.
Sec 90, 1 over cos 90 is also undefined.
Right.
And cosec 90 is 1 over sin 90, 1 over 1, which is 1.
Okay. So it's like the opposite of the 0 degrees.
Yeah, kind of.
Okay. Cool.
So our source has this table summarizing all these values for
Okay.
0, 30, 45, 60, and 90 degrees. Really handy, right?
Well, that's a good reference.
And one thing I noticed, as the angle increases, sin A increases,
Okay.
but cos A decreases.
Huh. Interesting, right?
Yeah, it's a good thing to keep in mind, I guess.
Yeah.
Yeah.
So now we've got some examples of how to use these values to solve problems, right?
Okay.
Like finding the missing sides of a right triangle.
Okay.
If we know one side and one angle,
Right.
it shows that if you know one side and any other piece of information, you can find everything else.
Okay.
So you set up equations,
Right.
use the trig values, and solve for the unknowns.
Right. Yeah. Just apply what we know.
Exactly. And then there's this other example where you're given a sin A, B, and cos A plus B,
Right.
and you have to find A and B.
Okay.
You basically end up solving a system of equations.
Oh, okay.
So you got to use your algebra skills here too.
So it's like a combination of trig,
In algebra.
yeah,
Okay.
and then exercise 8.2 has more problems like that to practice.
Okay, cool.
Okay, so we've covered the definitions, specific values. Now let's talk about trigonometric identities.
Oh, okay. Identities.
So what are those?
Yeah.
What exactly are they?
A trigonometric identity is basically an equation with trigonometric ratios that's true for all possible values of the angle.
So it's always true.
Yeah, it's like a rule, a fundamental truth.
Oh, okay.
They're super useful for simplifying expressions
Right.
and solving equations.
Okay.
So the most fundamental identity,
Okay.
sin A plus cos A equals 1.
Right.
How do we prove that?
How do we know that's always true?
It comes from the Pythagorean theorem.
Oh, okay.
Remember, in a right triangle,
All right.
ABC, AB plus BC all equals AC.
Right.
Now, if we divide every term by AC,
Okay.
we get ABAC plus BCAC equals ACC.
All right.
And AB over AC is cos A.
Right.
BC over AC is sin A.
Right.
And AC over AC is 1.
So we get cos A plus sin A equals 1.
Oh, okay. That makes sense.
Pretty neat, huh?
Yeah.
And from this one identity, we can derive two more.
Okay.
1 plus tan A equals sec A,
Right.
and cot A plus 1 equals cosec A.
Okay.
So those three, they're like the big three.
The big three. Got it.
And they let us express any trig ratio in terms of any other ratio.
Oh, okay.
So if you know one, you know them all.
Right.
And our source shows an example where tan A is 1 over 3.
Okay.
You can use the identities to find the other 5 ratios.
Right. Right.
Now we get into proving more complex identities.
Okay.
It's like solving a puzzle, right? You start with one side of the equation,
Right.
and you use those basic identities and some algebra to make it look like the other side.
Okay.
There's some common strategies, like converting everything to sines and cosines.
Oh, okay.
Our source shows an example. Proving sec A, 1 sin A, sec A plus tan A equals 1.